Hi everyone, welcome to my channel Tech Tutorials 2K21, and today in this lecture we are going to learn about a single source shortest path using Dijkstra's algorithm in design analysis of algorithms. So before we are solving this problem, we try to understand the algorithm of Dijkstra's for constructing a single source shortest path, and we have to remember the points like here. Like for constructing a single source shortest path, so we have to consider a graph which consisting of non-negative numbers. And here it is an algorithm. So this is a priority queue based an algorithm. This algorithm is used for constructing a single source shortest path. And for that we are considering a graph which consisting vertices and edges, and which is a weighted graph and connected with all our non-negative weights. And its vertex is. So what the output we are expected is the length. So which will give you a shortest path from source to destination. So and here the penultimate vertex, that is PV, for every vertex in V in capital B. So like you can consider capital V is nothing but all the vertices of your graph, and the small v will consider the vertex which you are going to visit. Now you can consider from this vertex and you are going to see all the remaining unvisited vertices from this. And then we have to take the weights of that. And we need to update those weights for constructing a shortest path. And initially we are going to initialize the vertex priority queue to empty. So because there is no vertices, so that we have to set this queue as empty. And then we can start for each and every vertex, we need to find out the distance from the vertex to that vertex. So that is from V in capital V do. So like initially the distance from that vertex, we can make it as a infinity. And then your penultimate vertex PV is also consisting null. So this is an initial state. And later what we have to do, we have to insert into a queue. So that is of your priority queue. And we have to insert that vertex along with the distance from that vertex. And now initially ds is 0, means which is the source vertex you consider, and that vertex, the distance we are considered as 0. And then capital Vt is nothing but the vertices we are including in a single source shortest path is also considered as null, because at that state we don't have any vertices. And then we have a function that is a decrease q, and this is your source, and this is the distance from source, and we have to update the priority of s with the distance of s. And we can run this loop from initial vertex to n minus 1 vertices. And here we can see capital V is nothing but all the vertices which is already visited. And up to this all visited vertices, we have to run your loop. And here U star is nothing but the vertex which we are going to delete from the queue. Okay, and capital VT is nothing but all the vertices, and we are including this deleted min q is also to your visited vertices. And for every vertex U in V minus VT, so that is nothing but all the vertices, and we have to remove all visited vertices. Now you can see the unvisited vertices. So from that what we have to do, so we have to see all adjacents of the vertex U, and we have to find out the distances. Like how we are going to repeatedly find out the distance for that deleted vertex, like you have to consider the weight on that path. Okay, and then previously the weight what we are already find, and we have to consider those weights. And among of these weights, which weight is less than, and you have to consider that weight and you have to update that weight to your weight of the vertex u. And then you have to update that penultimate vertex also, because this vertex we have to consider for the next step. And then we call the same procedure like same function decrease function, which is used to update the weights of your vertices. So this is a Dijkstra algorithm. So simply we can say we can start from any one of the vertex and we treat as a source. Okay, we can start from any one of the vertex and we can consider it as a source. So from that source, we are trying to find a path to your destination. Okay, so what we have to do, we can do two steps here. For every vertex, we can update the weights. Okay, so as of that vertex, what is the weight we have, and we have to update and we have to move on. And here it is a simple example. And by this example, I try to understand how you're going to construct a single source shortest path using the Dijkstra algorithm. And now you can see this is a directed and weighted graph, and you can see some directions are there. And then each and every edge is having some value. So here in this example, you can consider any one vertex as your source. So from that source, you can reach any of the destination. So here we consider A as a source vertex. Okay, and then from this, we are going to find out the shortest path to reach your destination vertex. And now you move on to construct of single source shortest path. And here you can see this is your starting vertex. So I consider A as my starting vertex. And here the weight of this vertex is 0 because from here I'm not connecting any one of the vertex with the edge. So the weight of this vertex is 0. So now I'm trying to visit from A to all the remaining vertices. And this is a weighted graph. So now all your outgoing edges will show that we are going to connect from A to that particular vertex. And all the adjacent vertex of this A is D and D. These two are the adjacency vertices. So now you can consider from A to B, right? So I have a path from A to B and the weight is 3. So now you're going from A to B with a weight of 3. Okay, so this is. And now I'm going to C from A to C. And now you can see you can update this weight. Let us you consider you can reach from A to B. And the distance from A to B is 0 plus 3. That is 3 here. So as of I can reach B with a weight of 3. And then here I'm trying to reach C. But as of now, no other vertices are visited. And from A to C, I don't have any path. So I cannot make any distance. I can treat as an infinity. So now you can consider the weight of C is mean. The distance from A to C is infinity. And here you can see the weight of D is 7. So because here I have a path from A to D and the distance from A to D is 7. So now you can see this is 0 plus 7, that is 7. And after that from E also, from A to E, I don't have any direct path. And then now the distance is infinity. Now you can see this is a representation of all the remaining vertices from A. So now as of this, we see that we have a path from A to B with a minimum distance. Now you can connect these two. A, B is connected because it's having the minimum distance. And after that, we are considering this, right? And now from this A to B, now I'm trying to reach all the remaining unvisited vertices, that is C, D, and E. Now you can see A to B, and after that, I'm trying to visit C. What will be the distance here? So as of now, the distance is 3. So now I'm going to visit from B to C here, and here the weight is updated. So now this 3 plus 4 is added, And now the infinity is updated with a weight 7. Right? Weight 7. Because I have an edge from B to C, I can move. So now what is the weight? We can add these two weights, that is 3 plus 4 is added. Now I get the weight is 7 and the previous it is infinite and it is going to be updated. And after that, you can see that from B to D. So I cannot move from B to D. It is not at all possible. So I can't move here. So still it is infinite. Okay, now I can reach from B to D. I can't reach. So this is infinite. And from B to E also I cannot reach. So now the value is again infinity on. So now here you consider the minimum distance is 7. So now you can update this and you can consider the next is from D to C. So you can consider the next shortest path A to B and then B to C. So from that B to C, and you can see all the remaining unvisited vertices are D and E. So now you can see there is no possibility you can move from C to D. Okay, because there is no edge which is connected from C to D. So now it will make it as infinite. And from C to E, so I can, and as of now the weight is 7. And now consider, so this 7 plus 6 and the infinity is updated with 13. So this value is updated 13. And now consider this also. Okay. And after this, so all these vertices are visited, like A, B, C and E is visited. And as of now, the D is not visited. Right. And now I can see from E to D. Okay. And here the weight is 13. So now this weight is added and we are getting this value as. So this infinity is going to change with 13 plus 4. That is 70. So now you can update this and you are going to connect this. So now you can see the shortest path from A to D. Okay, the shortest path from A to D, including all the vertices, is 17. Okay, so this is your shortest path. And the same thing you can draw like this, like from A, here initially the value is 0 and the weight 3 is added, now it get 3. And after that, here the weight is updated and 3 plus 4, it is 7. And then it is 13 and then it is 17. So this is a shortest path solution. Thank you.